Hello guys, welcome to my presentation on my proof. My name is Kim Duong, and I'm going to prove that a Dieudonné vector space is a metric space with the distance as listed. And, some of you have asked me since seeing the presentation schedule, well, what is a metric space and what's a Dieudonné vector space? Well, we're going to go over that as well as going over the Cauchy-Schwarz inequality and how it is involved in proving this. So what is a metric space? Well, a metric space is actually an ordered pair between a set and a distance metric on the set. So the distance is the Cartesian product between the set to the real numbers that results in a distance scalar, such that for any elements in the set, the following conditions hold. You've got non-negative distance, and that if the distance is equal to 0, this implies that x is actually equal to y. You also have symmetry, so the distance between x and y is the same as between saying the distance between y and x. And you also have the triangle inequality, so you have 3 points. One distance between 2 points is always going to be shorter than the sum of the other 2 distances. So perhaps you might need some help with the visualization. So symmetry is saying that the distance between x and y is the same as saying the distance between y and x. And the triangle inequality visualization, if you just ignore this, because I can't get that to go away, says that between 3 points, the distance between 2 points is always going to be shorter than the sum of the other 2 distances. So for example, this is a right triangle, so we know that the diagonal is going to be the shortest piece. But if you make this triangle not a right triangle, it should still work out. So then, after covering what a metric space is, well then what is a Dieudonné vector space? A vector space is a set E with vector addition mappings and scalar multiplication mappings, satisfying the conditions of element commutativity and association, the existence of an identity element and inverse elements, scalar distribution over elements, and element distribution over scalars. I know it sounds a little confusing, but it's just everything you would think would, work out. Here, the elements of E are actually going to be called vectors, or points, while the real numbers, lambda alpha, are scalars. With a vector space, there's also a mapping known as the dot product. So you take a pair in the Cartesian product and you map it to a real number that results from the dot product, such that for all x, y in E and alpha in R, the following hold. We've got E1, which is commutativity, so y dot x is equal to x dot y. E2 is distribution. You've got right side distribution and left side distribution. E3 is scalar independence, so if you have alpha x dot y, it's the same thing as dotting x and y first and then multiplying by alpha. And E4 is the positive dot product. So for any vector that's not the 0 vector, x dot x is going to be greater than 0. So we have more information. We call our vector space a Dieudonné vector space as defined in the higher geometry textbook provided by Professor Anton. You may recall from Calc 3 the use of a dot product, where E was actually equal to R to the n, and elements look like this. So when you dotted them, you actually had to multiply the components and add them up. So for example, this vector dot with this vector yields c1d1 plus c2d2, all the way up to plus cn/dn. A little confusing, but for example, what if you had the vector 1, 4 dot with 2, 3? Well, this is actually going to equal 1 times 2 plus 4 times 3, which is 14. It's not necessarily the case that a Dieudonné vector space uses that specific dot product. In fact, any product satisfying the conditions may be used. The dot product from Calc 3 could also be written as x dot y is equal to the square root of x dot x times the square root of y dot y times cosine theta, where the square root of x dot x is the magnitude of x, and similarly, the square root of y dot y is the magnitude of y. For cosine theta equal to 1, x dot y is equal to the magnitude of x times the magnitude of y. Using this, the Cauchy-Schwarz inequality prove that x dot y is less than or equal to the magnitude of x times the magnitude of y, and it holds for all vectors in R to the n. This particular example only proves that the inequality holds for R to the n, but the inequality actually holds for all vectors x and y in a vector space over the reals with a dot product mapping. Now, on to the proof. You might have forgotten, but what I'm proving is that a Dieudonné vector space with E equal to R to the n is a metric space with the distance x to y is equal to the square root of y minus x dot y minus x. Hence, the following conditions must be met. Again, they were non-negative distance, the identity of indiscernibles, symmetry, and the triangle inequality. I used a couple lemmas in my proof, which are provided in the write-up. The first lemma was that the scalar 0 times any vector in E is equal to the 0 vector. And the second was that negative 1 times any vector in E is the additive inverse of that vector. So on to non-negative distance. To prove non-negative distance in a Dieudonné vector space, we find the distance by cases. So you either have x is not equal to y or x is equal to y. If x is not equal to y, then by subtraction, y minus x is not equal to the 0 vector. By E4, which stated that if a vector is not equal to the 0 vector, the dot of itself is going to be positive. Hence, y minus x dot y minus x is going to be positive. Hence, the distance between x and y, which is actually the square root of the dot product, is going to be positive. Now, if x is equal to y, then y minus x is equal to the 0 vector. Thus, the distance between x and y is actually the square root of the 0 vector dot with itself, which is equal to the 0, so the square root of 0 is 0. So, you have the distance is either positive or equal to 0. Hence, it follows that the distance is always going to be non-negative. Now, what about the identity of indiscernibles? So, if the distance between x and y is equal to 0, this implies that x is equal to y. So, how to prove this? We assume that the distance is equal to 0, and you suppose that x is not equal to y. Well, we just showed that if x is not equal to y, then the distance is going to be positive, contradicting our assumption. So, if the distance is 0, then x has to equal y. On to symmetry. So is the distance between x and y the same as saying the distance between y and x? Well, note that by scalar distribution over elements in a vector space, since y minus x is in E, by manipulation, y minus x, which is equal to negative x plus y, just by switching this, which is equal to, as shown in my lemma, negative 1 times x plus, here 1 is obviously equal to negative 1 squared, so it's negative 1 squared times y. You can pull out that negative 1, and you result in negative 1 times x minus y. So since these two are equal, this is going to be an E. So using this, we can demonstrate symmetry. So we have the distance between x and y, which is the square root of y minus x dot y minus x. By subbing in our lovely negative 1 times x minus y, you result in this dot product. Now, remember that scalars are independent, so you can actually take this negative 1 and pull it out, leaving behind the x minus y in the dot product. And since the dot product is commutative, you can move this to the other side, right here. And again, by scalar independence, you can take out this -1 to result in -1 squared, leaving behind x minus y dot x minus y. See where I'm going with this? Your result is going to be x minus y dot x minus y by itself. And this is equal to the distance between y and x. So we have distance of x and y is equal to the distance of y and x. Hence, symmetry holds. Onto the last condition is the triangle inequality. So is it true that between 3 points, the distance between two of the points is going to be shorter than the sum of the distances of the other ones? So to prove the triangle inequality in a vector space, take the distance xz, which is equal to z minus x dot z minus x is under a square root. Add in -y plus y. This is equal to the 0 vector, so this doesn't change anything. For simplicity, because this can get confusing, let A equal z minus y and B equal y minus x. So this would be A, and this would be B. And just remember that A and B are in E. So then, by squaring it, so getting rid of the square root, we're left with just what's on the inside, which is actually A plus B. So A plus B dot with A plus B. Oops, A plus B. And again, by distribution, because of the dot product distribution product, you can FOIL this. So you're left with A dot A plus B dot B, which is plus 2A dot B. So again, A dot A plus B dot B plus 2AB. By the Cauchy-Schwarz inequality, you can actually note that this A dot B is less than or equal to the magnitude of A times the magnitude of B. So if you just make an inequality, the distance squared, which is equal to this, is actually going to be less than or equal to this. Because we know that A dot B is less than or equal to the magnitude of A times the magnitude of B. And let's call this inequality INQ. Setting that aside, observe that the distance between x and y plus the distance between y and z, quantity squared, by FOILing, you can yield the distance of xy squared plus the distance of yz squared plus 2 times the distance of xz times the distance of yz. So again, FOILing. By substitution, distance of xy squared, which is equal to y minus x dot y minus x, is actually equal to b dot b. And the distance of yz squared is equal to z minus z dot y minus z. I'm sorry, z minus y dot z minus y, and is equal to a dot a. Hence, the quantity squared, which is equal to it FOILed, by subbing it in what we know, it's actually equal to a dot a plus b dot b plus 2 magnitude of a times magnitude of b. And lo and behold, that is on the right side of our inequality. So, using this INQ, the right side of INQ is actually equal to the quantity squared. And remember that the left side is d of xz squared. So rewriting it yields d of xz squared is less than or equal to the d of xy plus d of yz quantity squared. Now what can we do with this? You think automatically to square root, right? Well, we know that the distance of x between x and z is non-negative as previously shown. So since the distance between x and y plus the distance of y and z is the sum of non-negative distances, it is also non-negative. So by applying the square root to both sides, the inequality is preserved. So then, as a result, we have the distance of x and z is less than or equal to the distance of x and y plus the distance between y and z. So the triangle inequality holds. So then, we nailed it. We got all 4 conditions to be held. So that means the Dieudonné vector space is a metric space. Thank you. Do you have any questions? well, of course, I need to do my spiel about the journey and why I picked this proof. I actually picked this proof because I really liked it, and it just kind of felt so simple, especially with the thinking. But it actually turned out to be a lot harder when I started trying to present it. I'm going to show you guys, I guess, my journey of the number of edits I received. So this is my first proof. In my textbook, quote unquote textbook, the dot product was actually represented by a vertical line. And the distance was actually, it almost looked like an absolute value between y minus x. So that was obviously confusing already. And Professor Schwall suggested that I turn to the normal notation, which I then did. And I guess it made everything a lot easier from there because this was just tedious. But something that really stuck with me from my first edit was that when I was trying to prove the triangle inequality, I used something really backward, and her comment here really changed how I looked at it. The logic here is backward. You can't start with what you want to show and end with a true statement. That doesn't prove anything. This only works if every line is an if and only if, meaning each step is reversible, and if so, you definitely have to state that. And like, I'm used to things like if it's an equal sign, obviously you can end with something true and work your way backwards, but I just really didn't know how to do this because I had proved it that way in my report. I got an A, I don't know. So then I just had to start fresh, and it kind of wiped away the fear of having to, start from scratch and work your way back up. So then my second edit used making all of these bold, first of all, which was ridiculous. It involved like a new command and a lot of different comments. Then going down the page, and then even more, which I was really excited when the arrows started disappearing, except right here they did not go away. And then even more. Slowly the first page started looking really great. I added in my definition of E and these two lemmas that allowed me to prove symmetry. And then, oh man, I was so excited for this one. No arrows. Oh, only a little comment. Little comments everywhere. This one, which really emphasized, am I using the Cauchy-Schwarz inequality in the general case or just the R to the N case? I got really hung up on that because I knew it worked for the R to the N case, but I had to look up if it worked in the general case, and it does, which is why I was able to use it in my proof and have it be accurate, as well as understanding the difference between the zero scalar and the zero vector. I just didn't want to go back and bold all the zeros, to be perfectly honest. And this was the latest edit, which really only had a couple comments on it, which was incredibly exciting. I really liked being able to submit a bunch of proofs. I mean, submit one proof and have it just edited. I mean, I was really hung up on it being like only 2 pages. I'm actually still really anal about this one page being only 1 page so that my proof continues onto the next page. Before, my page would end like maybe about half page, but it continues into the 3rd page, and all of these details were just really essential. And I really like that there's just so much detail went into everything, that every line wasn't meaningless. So I suppose that is my narrative for this proof. And thank you. If you have any questions, please comment below, make a discussion. I'll try to answer them.